Hi, you guys. My name is Stephen, and on behalf of myself and my entire corporate legal defense team, Maddie and Carl, I'd like to welcome you back to my calibration channel. Today I want to talk about how Endress and Hauser is selling what they say is the world's first self-calibrating temperature device. And I want to talk about why that's very exciting news for calibrators and measurement people, but also is going to be very challenging. I want to do this in 6 slides, so stick with me. First of all, we have a picture of the device itself. It looks like any one of a number of measurement devices that might be attached to an autoclave or a fermenter or what have you throughout the industry. It's amazing how much trouble can get wrapped into a device that's so small you could hold it in one hand. Here we have a schematic for what I think is going on in this device. And I must say, I think it's really elegantly conceived and designed. First of all, down on the business end, you see 2 elements. One's a PT100. These have been around for decades. They're very precise and very well characterized. What's new here is that Endress and Hauser has bonded what I call a traceable Curie point temperature switch right onto the PT100. I'll explain why it's traceable and how it works in just a minute. Now up above you see enough software and hardware to execute, manage, and save a whole bunch of calibration events that occur in this device right there on board. So how does the switch work and why is it traceable? 120 years ago, Pierre Curie discovered there was something really cool about permanent magnets. He found that if you raise the temperature of one above a critical value, it stopped acting like a magnet. Its ability to act like a permanent magnet resumed the minute you went below that temperature. In modern terms, we'd say the magnetic moment of all the atoms was aligned below the critical point and got all discombobulated above it. Now you can see from my drawing that this particular device trips at 118.0 degrees centigrade. And the fact that it's reproducible and precise allows us to tie a temperature standard to it, which links us all the way to the IS. Now what does Endress and Hauser mean by self-calibration? Well, let's take, for example, if we were to install this in an autoclave. Here we have the autoclave cooling down from some temperature peak. It passes through the device critical temperature, which in this case happens to be exactly 118 degrees. When that happens, the software queries the PT100 and says, we just passed through 118 degrees. What temperature do you think it is? It takes any difference between those 2 readings and calls it calibration data. If the difference is below tolerance, you're good to go. If the difference is above your tolerance, you're still good to go, but it will notify the system, we just had an out of tolerance in the PT100. It's already been recalibrated. Now that's the essence of this instrument. Every time this device passes through the Curie point in either direction, you recalibrate. You also save the documentation from that calibration activity, so it can be downloaded later. Were we to buy this device in Pharma, I can think of 4 different groups of people that would want to be at the table. First group is quite obvious. It's the change control guys in QC or QA. From their point of view, we might look at all the switching that's going on as unauthorized and unscheduled activities against a validated instrument. They might say it's unauthorized because there's no signature from a supervisor saying, yeah, calibration tech, go out and calibrate that device. It happens on the fly. They might say it's unscheduled because there's no work order associated with this activity. So are these reasons enough for a change control guy to choke on this proposal? I don't know. Next group at the table is the validation crew. They validate software, they validate hardware every single day of the week. They've never seen this configuration before. How are they going to do with it? Well, you know, if you just laid off 60% of the validators in this group 5 weeks ago, one of the survivors might come to your meeting and say, we understand what you want to do, we don't have the horsepower to support it. Get back to us in about a year when we've rehired enough validators to handle this. Next group at the table is the group that's closest to my heart, and that's the facility operations guys and the calibrators. At the very least, if we buy this device, there's going to be a bunch of calibrators rewriting a whole bunch of SOPs. And there's something going on in the background that's very interesting. Essentially, Endress and Hauser says a single point calibration for this device at a fairly high temperature will allow you to use it across a very wide range of temperatures. Suppose we stick this thing in a fermenter. Now, are we not only concerned with steam sterilization, which does happen around 118 degrees, but we might also want to run it at 37 degrees centigrade or lower. Is that single point calibration enough to assure us of temperature control at far different temperatures? I would recommend that anybody that buys this device and has that kind of question would involve their calibrators in figuring out an answer to that question. It would be fun to work on. The last group at the table is the group that's always in the caboose when a train like this rolls through the station, and that's the IT group. If we buy one of these devices, it's going to have no appreciable effect on our bandwidth. But what if we want to buy 40 of them? We want to put them in all our autoclaves. We want to put them in the 35 fermenters that we have on site. Our bandwidth requirements are going to explode. In fact, this situation makes me think that the Internet of Things camel has finally got his nose under our tent. The IT guys would probably be like a year or 2 or 3 years before we blow up their bandwidth requirements. Are we going to give it to them? I don't know. Okay, guys, one slide to go. I want to introduce it by talking about my favorite aphorism, and that's this. You can do a whole lot if you don't need credit. Now, I don't need credit for this idea because it came from Dan Collins in an article he wrote in 2011 in Pharma Manufacturing magazine. Essentially, in the terms we're using today, he said put 2 PT100s in the same probe, put it in the process, and then use each PT100 to monitor the performance of the other device. As long as they agree, you're cool. If one starts to drift, you use the other PT100 to detect it. Dan made his argument using Monte Carlo simulation and control charts, but he convinced me that theoretically he had a way to detect calibration drift long before the device went out of tolerance. Now, Endress and Hauser brings us the hardware and the software to complete this picture. Endress and Hauser's device is not detecting calibration drift. It's blowing it out of the water by recalibrating 5 times an hour. Dan had a way to detect calibration drift, but there was no hardware realization. So if we combine these two ideas, we're going to have not only what is a very powerful sensing and control device, but one that will provide calibration stability that we cannot achieve any other way. I think it's pretty cool. Speaking of cool, one of the cool things about these videos is there's a 10-minute time limit. So I think my time is almost up. I'd like to thank you for your participation. Please leave me comments if you care to. Please leave me ideas that you would like to hear me talk about, because I'm going to be making more videos anyway. Thank you.